So it has come to this. This is the summary lecture and some pointers on what the exam will include on the course software maintenance. So without further ado, let's get started. So this course has run for the 14 weeks. Now the seminars ended last week, and now the only thing left for you is to do the exam on the course Moodle webpage. Of course, you can also already see that the exam is there, and if you try to enter it, it gives you an error message. And in this lecture, the idea is just to quickly go through all the things we have covered on this course, so that you get a sort of an idea on what to expect on the exam questions. There will be also a couple of pointers and a sneak preview on the actual exam at the end of this presentation. So if you are anxious on what you actually should be preparing for, then I'd recommend that you at least watch the last part of this presentation. So, unlike other lectures, this lecture really does not include any new information. We are going to do a quick recap on everything that was discussed on the previous theory lectures, and we will not dwell for a very long time on each of these slides because the things are explained in details on the corresponding lectures. This is just to give you an idea and a brief outline on everything that happened on this course. And of course, if you are a new student and want to have a sort of an idea what to expect on this course, this lecture also serves for that purpose. So we started with really the fundamentals. Everything we do on this course is about software system, whether it's an application for mobile phone or normal office application on your computer or service site or website or whatever. It's more or less a system. It's made of components which have objects which have source code in them, and they have connections and they have hardware, they have things which they are connected to, and they exchange information and messages between these things. On this course, the central theme was on how to keep these systems alive, how to keep them functional, how to keep them in an order where we are certain or at least know beforehand how well they work and what happens or what we should do if they cease functioning. So, more or less, when the product is completed at the first iteration, when the development cycle ceases, the product goes to acceptance testing. Of course, on several courses before this one, this was the end stage of the product development. The acceptance testing means that everything exists, everything is connected, everything works as intended, and we are just ensuring that things happen as they should be. But on the maintenance course, this of course was more or less the first step, or rather more realistically, the end of the first iteration of the product. When we start to do the actual maintenance, we have to do changes, fixes, additions, these sort of things to the product, meaning that when the product leaves acceptance testing, it's not complete, it's only the first base level of the product which enters a maintenance phase. So in general, we extended this software lifecycle idea. Not only, of course, software development or software product development or service development always starts with requirements analysis, specification, and design. Then comes the development and quality assurance work, testing, and regardless of the actual process we apply, it more or less is in modern days iterative approach where we do incremental development until we have something that fulfills all the requirements and the customer likes it. The software process part, as it's traditionally explained, starts with the requirements analysis and ends with the acceptance and operations. But if we talk about software lifecycle, like we do on this course, it also includes the steps of maintenance and finally at the end stage of the maintenance, the end of life support activities. For example, on the seminars, we saw a couple of examples on products which were getting close to the end of software lifecycle and were more or less on the last legs of their development. This, of course, means that if you are taking the software engineering methods and models and software maintenance courses together or right after each other, like you are supposed to do if you are in our program, the rough division of how on what we are focusing on, or what are the techniques and skills we are talking about or learning on this course, are divided as is. So there's a number of different maintenance types: corrective maintenance, adaptive maintenance, perfective maintenance, and preventative maintenance, which are the ones which are more or less defined on all typical materials. There's also a couple of other things mentioned. For example, on the corrective maintenance, where we are correcting errors, there's also emergency maintenance, which means that it's an unscheduled emergency work which tries to more or less band-aid the thing together so that it can be fixed when on more controlled fashion later on. Also, on the perfective maintenance, we are not only adapting or making changes for the system so that it meets the new user requirements. We have another way of seeing it as an additive maintenance, where we increase the amount of content or things to do with the product without actually making any real changes on how the system behaves or how the user interface behaves, or what sort of activities the user can do with the content. Also, going from these different types of maintenance work, we also talked about the quality in the first parts of the course. So this model by Regnell et al., which was introduced in the IEEE software journal, more or less gives the idea that you can always have more quality. But on the other hand, at some point you have the saturation breakpoint, which means that it's not useful to try to polish the product more. There's always two sides of the coin. You need to have certain amount of quality or certain amount of maintenance work to keep the system functional and competitive and something that your users like to use. But also there's a possibility that if you keep dabbling with the product too much, you are just wasting time and money or your organization's resources just trying to make something better that really no longer benefits on these types of additions. And for understanding how the different quality characteristics happen, there's, for example, the ISO IEC 25010 quality characteristics model, which defines for quality in use and product quality with the different attributes and sub-attributes or quality characteristics. This, of course, is by no means the only way of defining things, but this standard-based model is something that's fairly universal, in a sense that it can all be applied in many different types of software products or services or things. It also accounts for the differences between the production values and the value for the user, meaning that you can measure both sides of the things, the user experience and the inherent quality of how the product was made or designed, or how much money was used or resources was used on the development work. Of course, if you consider these different models, you have to always keep in mind that there's no one definition of quality. It also means that on all products we ever are going to use, all the different quality attributes are more or less somewhat useful. Some of them are in some scenarios useful than others, but still there's not a real question of what quality characteristics are useful in, for example, mobile game or browser-based web store or something like that, they all need everything in this list, but it's just that the intended use might actually set some quality characteristics to become more important than another. And this is actually fairly interesting, that even the people doing the development work don't necessarily consider that this and this quality characteristic is important for this product. It's actually more about what they are doing to the product. Are they making the user interface design or database design or security design or whatever that more or less affects their viewpoint on the important quality much more than what the general user opinion or user perspective might be. So in this sense, keep in mind that the universal common good quality is a myth. You have to define what you need to measure, how to measure it, and how to use this measurement to improve your product, your process, and your maintenance activities. Also, we discussed something about best practices and how to use version control. This slide here is about what are the best practices for agile developer, since in several occasions it became apparent that the maintenance cycles are more or less just mini software production or software development cycles. So what works in the development of software also tends to use in the maintenance of the software. And the best practices of agile developers, or the checklists of where the different problems are, or how to use version control effectively, are all very important things also in the maintenance cycle. So, for example, this list here is something that you probably see on all software engineering courses, especially if they are talking about software testing. So where are the problems? There are the new code, the new feature, the new technology, last change, last minute change, imported code, made by new employee, made for new client, so on and so on and so on. So this is also something that to keep in mind. If your patch or fix fails, you probably should take into account what was added or what was changed and why it happened. Also, why do you want to analyze or understand the structure of your product or your system you are maintaining? It's usually because the problems tend to accumulate on one or few different places. So if you understand and identify the problematic areas of the software, it usually makes your life easier in the long run. So if you want to measure something, then you have to understand what you need to measure. So there's a wealth of different types of measurements and metrics. They are available on the standardizations and other things. For example, in the materials provided in the additional reading library of the course webpage. But for example, if we want to measure something, we almost always have, well, basically always have to have these attributes for that measurement tool. It has to be objective, it has to be reliable, it has to be economical, and it has to be reusable. This is a fact of life. If your metric or measurement doesn't have all these four things, it's probably going to be useless. It doesn't give you correct results, it doesn't give you reliable results, it costs too much to be actually useful in real life, or you can't repeat it, so you have no measurement or comparison points to understand what the result actually was and where your project is or process is going. Of course, if we want to measure things, like I mentioned, for all the quality attributes and quality characteristics which were mentioned on the previous slide the diagram couple of slides ago about the different quality characteristics, there's also a way to measure or assess each one of them. Like in the lectures, we didn't go through them one by one because there's hundreds of them in the entire standardization material. But for if you are really interested in these things, you probably should go to Moodle pages or Google around for the standardization so that you get the idea on how to measure and how these different types of measurements in general are defined. Also, besides these measurements and metrics, there's a number of different things or indicators which are fairly universally used in software engineering. For example, the cyclomatic complexity, which measures how complex the structure of your module is. This is one thing. This is also something that was mentioned in a couple of the seminar presentations. This is something that the organizations really use to get a high-level understanding on what the complex parts, complex modules of the product are, and what are the parts that need to be watched if you are trying to maintain them. Similarly, Halstead's software science measurements are also something that gives you fairly good information or indication on the amount of work needed or how complex or difficult it is to fix or change something in the different parts of the software. This is more or less about the how much time it takes, so how much it would cost. And this, of course, is irrelevant for the developer who has to fix the bug, but this is very important for the project manager who has to wonder how you are going to afford or pay for the needed changes, and can't just give a blank check to developer to use as much time as is needed. Similarly, the entire point of different measurements is to be useful when we are doing regression testing. Of course, it has to be understood that maintenance work is development work, in a sense that sometimes these maintenance projects or maintenance cycles fail. In fact, depending on different types of software, what we are doing, the amount of bad fix injections is actually from 2% to up to every fifth of the patches which will fail. So if you are doing continuous development or continuous integration or these sort of things, it's not very unusual that you have to backpedal or take away something that was already sent or unpatch your product. It's just something that your software or system has to be able to support. Of course, this all goes along with the fact that we are constantly going towards more faster and more hectic development cycles. As with this history of software integration and regression testing slide, you can see that basically the waterfall and other things, plan-driven development more or less, started to shift or lose its importance in the change of the century and the millennia. And actually, it's more common nowadays to have agile projects. Agile approaches and agile mindset is actually going even to the high critical levels of software development. And of course, these definitions by, for example, Martin Fowler and Kent Beck, they have been defining different ways of supporting some form of highly agile approach without breaking down into cowboy coding or a horrible mess which we can't anymore control in any way. And these things, extreme programming, continuous integration, continuous deployment, continuous delivery, these all are approaches which try to minimize the amount of time between the situation where we need to add something or change something and we want to clear it for injection into the production software or integrate or deploy it to our customer. So basically, what we have to also understand on all these different processes and methods, and these are actually things that intensify when we are following more strict or quicker development cycles. Problems usually are connected to each other. So if you want to measure something, if you want to oversee something, or if you want to manage your project, you more or less have to understand that in a software organizations, there's human factors, there's experience factors, knowledge, there's machines, there's technology, there's all these different things which affect each other. So the problem might not be obvious. And that's why you need to measure, you need to collect information, you need to observe, and you need to manage your projects, because there's usually something that you might miss, and it might actually be even an important part or important step of activities. For example, on this example diagram, the obvious thing is to try to understand why is product design causing trouble with testing. Why is testing causing trouble with humans and organization? And then finally, why integration keeps failing or being a problem to itself. Of course, these are important parts, but they are not the only problems even in this diagram. So, going further, moving further from the process management and process measurement techniques, we talked about different aspects and different ideas and different concepts of software engineering and software development, which also obviously affects the software maintenance work. Technical depth was one of these things, which is a measurement, or more or less the name given for all the shortcuts taken, or the situations where we cause trouble further down the maintenance cycles by not doing things properly. Sometimes you need to have it, and it's actually usual that you will end up with some technical depth, but you also need to take into account that this is something that you need to fix further in the future. Similarly, refactoring was one of the ways of fixing things. If we have too much problems with one module or one part of the software, then we have to recreate it from scratch, make it work as it was meant to be, or recreate it now that we have more insight or experience on how the system around that faulty or troublesome module actually works. So we improve the internal structure and not touch the external behavior. Also, if we want to find places which are good candidates for the different refactoring approaches, there's things like code smells. Usual problematic things which usually indicate that there's a problem in this part of the system. So yet again, there's a huge list of definitions, so you need to go to the Moodle pages and get the original reference from the course lecture slides, and you can read the stuff there. It's very interesting and it's very useful information. Here is just a list of different patterns or anti-patterns which the code smells usually try to indicate and find out. So, going from these aspects, we went to talk about the reverse engineering. So why do we sometimes need to reverse engineer things? Of course, sometimes we lose information. Sometimes we really can't have things like which we used to have. For example, we might lose source code, or we might have to re-implement something on different platform, or we might have to recreate something that can handle the old databases or these sort of things. So on these occasions, the reverse engineering tools and reverse engineering tactics are usually employed to salvage the parts which are still useful, or salvage the parts which include the necessary bits which we need to keep alive. For example, for business purposes or something to this degree. Also, with the reverse engineering, there's also re-engineering, meaning that we make the system more maintainable. This means, of course, that we are doing some sort of refactoring, but instead of actually fixing some small part, we are redesigning everything and making it use, for example, the old database and the old things. This is what software re-engineering is all about. It's recreating a new part or making a modern part which is compatible with the old system, or for example can use the old database to retrieve information, or can use the old the customer interface and replaces everything behind it so that it works more fluently. Of course, making these sort of things is very expensive, and usually even more expensive than just replacing the thing with completely new stuff. So obviously these are not everyday occurrences in software engineering work. But on the other hand, on this lecture we also talked about different strategies on how to work with the legacy code, and when we need to reverse engineer something, and when we need to re-engineer something, and when is it possibly completely okay to just drop the old system altogether. So going forward from that topic, we talked about the different ways of trying to maintain software, or try to support software in an environment where we have several similar products, or we have long-term plans or long-living software product, which of course meant that we have to have software product lines and software configuration management. The software configuration management was more or less about the version control and how to manage all these different aspects. So the details are on that lecture. Please refer to that. Similarly, the software product lines, so that we develop core assets separately from the products, which may have some variation or tailoring to use the core assets, and the management of how to keep things flying is about trying to maintain a solid base for all the new products, where we only need to make the necessary changes to the existing components or the necessary additions to make new product out of our library of old things. Of course, this requires somewhat a different mindset than normal software engineering or software development process, because it also means that the core assets are developed with the mindset that we will be using these parts for a long time or in several products, so they have to have the different abstraction level considering purpose-built components. This is something that's not inherently different from doing normal software process development, but it's a new way of thinking and new way of designing the software architecture, where we have the high level or the optimized core assets, which you have the certain interface, and then the product's own assets, which apply these core assets correctly. On the next lecture, we talked about the different ways of helping the quality assurance and testing work. For example, the test automation and the different types of test automation generations was discussed. The idea is, of course, that we do some test automation to help or with the amount of manual work required to ensure that everything still works correctly and that there's no bad fixes in our product. Of course, on some occasions, the test automation might actually even cause more trouble. But if it works very well, if it's mature enough, then it takes away the laborious, repetitive monkey work out from the manual, out from the testing work. And this is also why it's fairly useful when it's done correctly. In the test automation, you always have to consider that if what you are doing is actually useful to automate. Do you need to make constant changes? Do you have money to maintain the stuff? Is this important enough that it will have enough use, or is our tool sophisticated enough that its usage doesn't actually cost us more money than doing the same thing again and again manually? And finally, on the test automation, there's the evolution from recorded scripts to engineered scripts and data-driven testing and keywords, and finally to the model-based testing. On the course lecture slides, we have examples of different levels of evolution in test automation. So if you don't remember what each of these things mean, go refer back to that lecture. And there's also a number of examples which you can follow or Google around on the internet to get an idea on what these sort of tools look like. The keyword-driven testing and the model-based testing for example, require a very different approach to development or quality assurance work than just recorded scripts. But on the other hand, the recorded scripts only are there to give some automation or quick way to run, for example, several test cases right after each other. So, when we entered the last part of the course, we were talking about the different maintenance stages. Programs age. Of course, it's not the source code which ages, because it's just instructions and formulas to complete different things, but it's clearly observable in all products that there's different stages. When the product is introduced, we try to emphasize user support. When we are growing, we try to correct faults. When we have stable user platform or stable amount of users or user population, we try to do enhancements to keep our users happy. And finally, when the time moves onwards, we try to keep the product working on new different platforms so that we are still competitive and try to offer possibility to run our product with the newer platforms and newer technology. So on the legacy software, like I mentioned earlier, there's a different approaches on how to do legacy software maintenance, and especially what to do with the legacy system that needs to be replaced. This was taken from the software aging lecture. You can see what these different things mean on those lectures, but there's a different ways of approaching what can be scrapped, what needs to be saved, what can be replaced, and what we need to re-engineer or reverse engineer and re-engineer to work in our new environment. Of course, usually this is also somewhat restricted by the costs. So this is one of the things that affects the decisions. And these different strategies more or less give you the possibility to formulate the most probable way that what should be done and what can be done. On the last lecture, talking about the different scientific background and information regarding the software development, there was some things like the Lehman's laws and software maintenance. So, okay, these slides or these laws and these laws more or less define all the different things that will happen to the software product or service or whatever app when we are using the software, or when the software is being used and it gains age, it needs changes, something needs to happen. People who have not been developing the software are maintaining it, and so on and so on and so on. So these more or less summarize everything. So it can be fairly accurately said that if you really understand why these laws are here and what do they actually mean, you more or less understand what this course is all about. So finally, before we go to the exam instructions, a couple of final words. These are actually taken from the first lecture. So of course, software maintenance is a major share of software lifecycle. It uses majority of the financial resources. It uses majority of the man-hour resources, even though sometimes the development cycle can be long. If the product is in any way successful, the maintenance will be the more expensive part of the software lifecycle. And we need to upgrade stuff because operating systems, databases, platforms, frameworks, these things keep changing because they keep evolving. And even if they wouldn't, our users find new things, they have new requirements, they have new ideas, you have new competition or competitor who does something differently or even better, or somewhere something is more fluent than our user experience. So we need to do modifications, we need to do additions, we need to do fixes, and this is all maintenance work. So even if there are some tools which are especially useful for software maintenance, for understanding legacy code or reverse engineering source code or doing something to this degree, software maintenance has the same tools, methods and techniques than software development. And of course also maintenance is required on all types of software, whatever the technology, technique or tool used to create it is. So basically there's this rule of thumb here. So it costs €1 to come up with an idea and a proof of concept. It costs €10 to test and develop a product from that idea, meaning that you have something that's acceptance tested and you can deliver it to your first customer or your first users can use the software. However, normally it might cost up to €100 to maintain and commercially support the product through its life cycle. So in that sense, it's a bit of a wonder why these software maintenance courses or software maintenance as a topic in many of the degree programs isn't considered that important, because it's the most costly phase of doing things, and it's also one of the most important aspects of defining whether this product will keep making money or just fade into obscurity, because no one likes to use faulty software. And finally, when you are doing research, or if you are considering becoming a researcher or academician or something like that, or even going to the industry, keep in mind that research of software engineering is research of software maintenance. And research of software maintenance is research of software engineering. These are part of the same thing. Developing software is the first step to get something that you can maintain, and maintaining is basically doing software development while your product is in use or in production, or you make money out of it and can collect metrics on the user behavior or user satisfaction or production data on how the thing keeps performing. So finally, to the last part of this course, the online exam. These are more or less the same instructions I have put on the Moodle webpage already, but the first exam of the course will be held on 10th of May between 12 o'clock midday and ending at the midnight of the following night, so 12 hours. When you press the button I want to start the exam, you have 3 hours to complete all the exam assignments which are randomly assigned to you. Although be aware that if you start with less than 3 hours before midnight, you will only get until midnight to submit your answers. So try not to cheese the system this way. It will not work. Also, unlike on many other courses, you don't have to enroll or register for the exam. Since you are already on this course and can see the Moodle pages, you are already registered for the exam and can take it, even though WebAudi doesn't show that you are are registered for the exam. So in the exam you will be assigned 6 of similarly difficult assignments from a larger pool of things, and you need to answer up to 5 of these assignments. Each assignment is worth of maximum of 6 points, meaning that your exam has maximum of 30 points in it. Only the first 5 submitted answers will be reviewed. You are allowed to leave 1 blank because you are given 6 assignments on which the 5 you need to answer. Leave the 6th one with the one you do not want to answer to blank. If it's in the middle of the exam, like the assignment 3, just leave the answer box blank and I'll skip it when I'm grading it. And like on all online exams, because I have no way of observing what other things you are doing while you are doing the exam, you are allowed to use any reference material available via internet or from the course lectures or from the additional reading materials from the course or from Stack Overflow or wherever. You can even work with a larger group because there's it's statistically insignificant possibility that you will be doing the same exam with anyone else on the course. But you need to submit your own work and you need to reference everything you include in your answer, including parts which you took from the course materials or lecture slides. This means that if you submit an answer which doesn't have its own list of references, you are doing something wrong. So always give a reference to where you got this piece of information. So you need to get at least 14 points to get a passing grade, and each 5 points from the exam translates to 1 point towards the course grade. You are allowed to use whatever tool or whatever technology or type of computer do you want to use to complete the exam, but it's your problem to complete it with a smartphone or something to that degree. I recommend that use a full-sized laptop or workstation with reliable internet connection, along with pre-installed tools which allow you to draw diagrams, write source code, and write technical essays. I have had, or our department has had, a complaint from a student who was working on this similar exam and complained that he was unable to complete the exam when he was traveling in Africa and trying to complete the exam on a smartphone over in the bus provided wireless internet connection. Please be not that person. Use full-sized laptop, reliable internet connection, and take time to actually seriously prepare yourself to answer to the exam questions. The maximum length of each answer is 2,000 characters, and the images, diagrams, and tables are counted as 400 characters unless otherwise mentioned. Also, list of references is not counted towards the maximum length of the answer. And like I mentioned earlier, all external sources and materials, including the course slides and additional reading materials, has to be referenced. I will use plagiarism detection tools on your answers, and we can and will use Turnitin and these sort of things to check or do random checks that everything is done as instructed. Please, you are allowed to use whatever materials you have. Try not to screw this up by trying to also sneak in some references which you didn't actually include. You are allowed to use whatever material you want. You just need to reference it in your answer. Finally, this is probably the thing you have been waiting for. This is the high-level topic of all the exams, the exam questions that are in the pool of questions that are included in this course's exam. So all these items include sub-questions. Remember to answer to each of them. If there are sub-questions, it means that they are taken into account on the grading, and each sub-question is a point or part of the point or something like that. So remember to answer to each sub-question. These are the high-level topics. If you have prepared yourself to give some sort of answer to all these different things, explain what they are, what the general idea is, how it relates to software maintenance and software engineering, you probably are on a solid platform and are well prepared for the exam. So that's that. Thank you for taking this course this year. So hopefully you'll all get a good grades and we don't have to do many additional work or paperwork. So good luck for the exam. You will be provided grades on your presentations and project works after the exam. I will go through all the submitted materials at the same time. And if for nothing else, thank you for participating, thank you for listening to these lectures, and remember to answer to the feedback survey, because that is the only way we know if this course works or not, what can be improved for next year, what we will keep from this implementation, and what we will redesign or re-engineer for the future implementations. The survey is the only way you can get your voice heard in a controlled manner, in a sense that we will actually get money and can appoint resources to things that need fixing based on your feedback. Because this course was also run for the first time, I hope that most of you fill the feedback survey so that we know what sort of things to consider or improve for the future reference. But anyway, this starts to turn to rambling. Thank you for participating. Good luck for the exam and have a nice summer period. Thank you.